Welcome everybody, and thank you for attending today's webinar. The need for therapeutic antibodies is greater than ever. SPR is the gold standard for characterizing antibody-antigen interactions. Now, with high throughput SPR, screening and characterization can be accomplished in the same step, which streamlines the drug discovery workflow. During today's webinar, if you have any questions, please send them via private chat to me, the host, John McKinley, and they will be answered at the end of the webinar. Now I'd like to introduce Dan Bedigner. Dan is an expert in SPR and modern-day antibody discovery workflows. He brings a wealth of knowledge after being at biotech companies such as Xoma, Abgenix, and diaDexus. Now he's leading our application science team. Hey Dan, I'll hand it over to you now.
All right, well, thank you, John. And thank you all for joining us today. So these are the topics that I'm going to talk about today. So we're going to start off with just sort of the fundamental principles of SPR and go over how the detection technology works, and then go into a little bit about the basics of principles of kinetics analysis and what the rate constants mean and what curves should look like. And then go over at least one example of best practices and talk about how surface density affects kinetic analysis. And then from that, I'm going to move into an introduction to high throughput SPR with the LSA and give an overview of the instrument, talk in some detail about the surface chemistries we have available, and give an analysis example from a recent publication. So SPR is surface plasmon resonance. And this technology works by we immobilize a binding partner to a surface. Well, we call that typically the ligand, the immobilized partner. And then another sample is injected, we call it in solution, and that is the analyte. And that's the other binding partner that can interact with the immobilized species. The actual detection technology works as diagrammed on the right here. So we have a laser-like light source that is focused in through the bottom of a prism that is coated with a gold layer, and then the other side of that gold layer is exposed to the analysis solution, the flow cell. The light is reflected off of the bottom of that gold layer and detected by a sensor. In our case, it's a large CCD sensor that collects essentially an image of the entire array surface. And so ideally, or the way that the light reflects is you get total reflection of the light off the bottom of the surface. So you see essentially a saturating brightness on the detector. However, there's an angle, the SPR angle, at which photons are lost to this evanescent plasmon wave in that very thin gold layer. And the angle that occurs at is determined by the refractive index of the solution on the other side. So as we vary the angle of incoming incident light, we get, and we collect frames, many frames per cycle as we swing through a fine series of angles of this incoming light source. The reflected light varies in brightness. So it goes from being fully bright to a dim spot as we approach that critical angle where the SPR photon, or the photons are lost to the SPR response, and then it goes back to brightness. So we observe that for every spot on the array on the detector. So the way we set up these experiments are we have a gold surface that has a matrix on it. Usually it's some form of hydrogel, and then we immobilize the ligand to that surface, and then under flow, we expose that surface to an analyte. This would typically be for the LSA, we typically immobilize the antibody onto the surface and then flow the antigen over the top. And then that binds and dissociates. And we can monitor that SPR response in real time across all of the interaction locations. So just to give a little bit more detailed example of how this works is, so we have the light source for the incoming light is varied across a fine angle. It's about 3 degrees. And here we see a plot of the data. So we generate one of these we call them SPR dips, for every ROI in the array. So we'll talk about this in a bit more detail later, but the LSA collects 432 ROIs at all times. And so we see if this is brightness in the y-axis and angle in the x-axis, as you scan across the angles, you have essentially saturating brightness, full brightness. And then as you approach that critical angle, the brightness starts to dip and then goes back up on the other side. And so the position of this dip is dependent on the refractive index in the solution above. So if you have a high salt solution or you inject glycerol, this dip shifts to the right. It will shift to the left if you have low refractive index. So say you inject water or dilute acid over the surface, that dip shifts to the left. Also, if we were doing a binding cycle, you can see, say we're at essentially rest position with a bare chip in buffer, and then we immobilize a ligand to the surface, we get a shift to the right of the dip because the binding of protein at that surface fluid interface changes the effective refractive index on the surface because you're essentially changing the mass of the molecules in that sensitive region to that evanescent wave. So it becomes very sensitive to protein binding to the surface. And then if you bind antigen, you get a further shift to the right. And then as that protein dissociates, the dip shifts back to the left. So the instrument itself records these Plasmon dips, but the user sees binding responses as they're translated by the acquisition software. So this is going to be sort of a schematic of how an experiment would run, where you can see what the instrument sees as these SPR dips, and then what the user sees as these real-time sensorgram, where we get a binding response in what we call RUs, or response units. It's essentially an arbitrary unit that technically does correlate back to a certain mass of protein binding on the surface. So if we're flowing buffer, we're getting a dip in a baseline signal down here in our sensogram. That stuff starts to bind. We get the dip shifts to the right, and we get an increase in our binding response on the trace. Eventually, during an injection, you'll hit an equilibrium where your response will plateau, ideally. And then as you switch to buffer flow, the proteins dissociate, and you can collect this real-time dissociation data. So what are the rate constants that we're recording, and how do we observe them? So the fundamentals of this is we have a simple one-to-one interaction where we have A plus B forms the complex AB. And this happens in a reversible orientation where we have the Ka, which is the association rate constant or on rate, driving the formation of that complex, and then the dissociation rate constant, the off rate, or the little k, little d, driving the dissociation. And the dissociation is always occurring. Well, essentially they both are, but during a binding cycle, when we switch to running buffer after the association phase, the concentration goes to 0. So the Ka term essentially drops out. The affinity of the interaction, or the big K, big D, or the equilibrium dissociation constant, is calculated by dividing the dissociation rate constant from the association rate constant. So in a typical global one-to-one fitting where we're doing a kinetic fit, we actually aren't directly fitting a KD parameter. We're extrapolating it from the off rate and on rate. So why is this interesting too, is another good question. And when you're looking at the pharmacodynamic effect of therapeutics, if you have a faster on rate, you can get a quicker onset of effect. Also, it can affect the ability to neutralize certain types of, if you're trying to neutralize, say, a cytokine that's circulating, having a rapid onset can make a drug more efficacious. and also start working faster. If you have a slow dissociation rate of an antibody, that antibody can persist in its physiological effects, after the serum level of the drug falls below what would be an efficacious range on its own. So you get this durability due to extended residence time on target and in receptor. Also, if you're trying to interrupt interactions that have very rapid kinetics, having a durable residence can be of advantage. And then a high affinity drug, just where your KD is a low value, means that typically you will get the pharmacological action at a lower serum concentration of the drug because you have higher occupancy at lower concentrations. So this is the schematic of a typical kinetic binding cycle where we have a baseline phase and an association phase. The association phase is determined by both the on and off rate components of the kinetic model. And then as the concentration goes to 0 in the dissociation phase, we get the KD, or the dissociation rate constant information. Diving into this a little bit more. So this would be an example of a typical concentration series where we have, say, a 3-fold dilution series of antigen. The concentrations are higher as you go up the curve. And the slope of that association is determined by the on rate times a ligand capacity term, essentially the Rmax parameter, or how much protein can bind to the surface, times the concentration of your analyte. And then all is involved is the off rate and the amount of complex that's already formed. So this makes the shape of the on rate phase a bit more complicated because there's 3 parameters that are affecting it: the concentration of the analyte, the on rate, and the dissociation rate. Then if you inject long enough or your kinetics are rapid enough, the interaction can come to an equilibrium. And that's where you see no real association or dissociation. You're at a steady state. You can see there's really only one injection on this set of sensorgrams here that has achieved that. The others are still climbing. You're just about getting there here. It's important to distinguish between equilibrium and saturation. Every concentration injection will eventually hit an equilibrium if you injected it long enough, but only very high concentrations would ever achieve saturation. And the timed equilibrium is actually dependent largely on the off rate. I mean, obviously both the on rate and the off rate affect it, but typically the biggest contributor is the off rate. And the equilibrium value itself can actually be determined not kinetically. So it can be described by this equation where you can use the KD term, and it's really an affinity-based thing. It's the timed equilibrium that's affected by the kinetics. Then as the concentration goes to 0, as we start flowing buffer, we have the dissociation phase, and the entire association parameter essentially drops out of the determinant, and we have this simple exponential decay based on the dissociation rate constant and the amount of complex that is formed at that time that you're measuring from. So the affinity of an interaction can actually be determined as an equilibrium or steady state. So if you have an interaction that forms, that comes to equilibrium rapidly, like in this example here, you can see all of these concentrations are essentially steady state. You can collect what we call a report point, a value in the steady state form, and then fit it to an isotherm using this equation and determine the KD of an interaction. The LSA software has a module for doing this. And it works well if you have transient interactions. So typically off rates in the 10 to the minus 2 range are about as slow of a dissociation as you can get where a typical SPR binding cycle will allow you to do this. In antibody screening and characterization, I see this approach most commonly applied for people that are screening Fc gamma receptor interactions, as many of them are quite transient. So in terms of actually fitting kinetic data the way we typically do, we use this integrated rate equation model. And this is a composite of sort of a slightly simplified version where we have the R equilibrium parameter, which I showed on the previous slide is over on the right-hand side, where we have the concentration of the analyte, the R max, and the KD parameter. And then you can substitute in for the KD, the affinity, the off rate divided by the on rate, and end up with the complete integrated rate equation shown here. In this, you can see there's 3 parameters that we float during a fit. There's the off rate, the on rate, and the R max parameter. So those are all global parameters to fitting the data to all of the sensograms. And the known parameters then would be the time and the analyte concentration. I should say during dissociation. During dissociation, when the concentration of A is 0, the equation simplifies to where we just have the response at a given time and then the off rate parameter with the delta T. So the interesting thing about the off rate is that you can actually measure it from essentially any point in the dissociation. The R max, or saturating level of the surface, isn't actually part of that equation. It's often why people would do off-rate screening conventionally, because from any point during that dissociation phase, as long as you're getting enough dissociation and you have a good sense of where your baseline is, you can fit the off-rate. So again, so the off-rate is this property of how fast the analyte dissociates from the surface, and it's measured solely, well, not solely, but it's actually fit in both phases, but it's best described in this dissociation phase when the antigen concentration is 0, and it's presented in the units of 1/seconds. So just to get a visualization of some examples, so about the fastest off rate you're probably going to ever describe with an antibody interaction is about 1/second. You can see the dissociation happens almost immediately from the surface, whereas a very slow dissociation example would be a curve shown here where we have a 1 × 10⁻⁵ off rate. You sort of bracketing range. There are antibodies that have dissociation properties slower than this. They actually become very difficult to measure with SPR. You can see that there's almost no visual dissociation in this 10-minute dissociation time shown here with this off rate. We actually use 1 × 10⁻⁵ as a default fitting limit in the LSA software. It can obviously be changed if you want to try to rigorously design an experiment that will elucidate more dissociation. But it's probably a good range for most assay applications because obviously, as you can see, if you're measuring almost nothing, any subtle change or variance will cause you to have a significant alteration in your estimated rate parameter and affinity. So when you design your experiment, you want to see decay in all your data sets, but you don't want to make every assay you run take forever. So we say, set it to something reasonable, but don't waste time. Usually, I'd say characterization assays are run with between 10 and 20 minutes of dissociation. That is good enough to get you down close to the low 10⁻⁵ range in terms of observable dissociation. And very often, if you're not seeing dissociation in that phase, just if you were to set it to, say, 35 minutes or 40 minutes or even an hour, it's unlikely that you would just all of a sudden overcome that and get enough data. So typically, if you're going to try to measure off rates down really that are very slow, designing a pretty robust experiment specifically to interrogate that parameter with lots of replication et cetera, is needed. I covered that in a bit more detail in the previous webinar. So when you're measuring the association rate constant, again, this shape is determined by both the concentration, the off rate, and the on rate. And it's while the sample is being injected and cycled over the surface. It's given as the Ka parameter in the units of 1/moles, 1/seconds. Some examples of that. So these are the same off rate shown in the same concentrations with a very fast on rate. This is about as fast as you're going to typically see antibodies, about 1 × 10⁷. And then this is actually a little bit slower than the typical you would see in a panel of specific binders. This would be a very, very slow association, probably ranging into the range of non-specific interactions. But you can see how the dose response of these concentrations changes as the on rate goes down. So knowing your off rate. So this is just an example of the same on rate, so sort of middle of the road for an antibody, 5 × 10⁵. The same concentrations and varying the off rate where we're stepping it up an order of magnitude slower with each plot. So you can see 10⁻², you're starting to get a longer tail. The injections are still largely coming to equilibrium in 5 minutes. And as we go to 10⁻³, this is getting more into your single-digit nanomolar typical affinity for antibodies. You still get easily measurable dissociation. Your low concentrations are no longer coming to equilibrium. And then as you go higher, you can see that you're a very long ways away from equilibrium in your low concentrations, but you're seeing more binding from the low concentrations as well. And this is a good example, too, to look at between the 10⁻⁴ and the 10⁻⁵ parameter. How much absolute difference is there in dissociation in this 10 minutes? I mean, it's clearly measurable. The software would give you a very good estimate of this if this was the data, but you can get a sense of the scale that even relatively subtle changes start to make significant impacts in your estimated dissociation when you get to that slow range. The similar slide for the on rates. So we're using a fixed off rate of 10⁻³ and varying the on rate as we step down. So you can see the dose response of the different concentrations really changes as the on rate slows. And also, it may or may not be obvious, but it's much harder, even for people that are really experienced SPR users, to just look at a sensogram and estimate the on rate, because it's affected by the 3 parameters. So you have to have a very sort of inherent knowledge of what are the concentrations that are being injected and what is the off rate and how that affects the shape to be able to intuitively see it. Whereas somebody who's done this a lot can look at a sensorgram and give you a pretty close ballpark estimate of what the off rate is, but that's just not true for on rate. It's such a more complex phenomenon. Okay, so now we're going to move into a description of the LSA platform. We call it the Lodestar array, and it's this benchtop high throughput SPR array system. So what makes the LSA so ideally suited and such a step up in throughput for SPR is that it has these 2 relatively independent fluidic systems that address the same sensor chip. It has a 96-channel flow manifold that we call it's a continuous flow microspotting technology. We often refer to it as the printhead. And then there is also a single channel flow that does what we call one-on-many, where one sample is injected over the entire surface of the array. So with this 96-channel manifold, it can do 4 nested prints to create a 384-spot array. So we're going to go into that in a little bit more detail here. So this is a visualization of that 96-channel side of the instrument where it was accessing samples from a 384-well microplate. And then the sample is flowed over the surface of the chip. This is that continuous flow microspotting, and really the big differentiator between the LSA and past array systems, whereas typical array creation is a deposition-based process where stuff's just being added to the surface. Here, the sample loading occurs under full flow. So it goes from running buffer to sample back to running buffer. So you can do all of the chemistries that you would typically do on an SPR biosensor, and you can do charge-based pre-concentrations to immobilize from low concentration samples. You can make an affinity capture surface and then flow for an extended period of time low concentration crude samples to concentrate your ligands onto the surface. So you're saying capturing from a supernate or a bacterial extract. The interesting aspect of the CFM is that, one, it flows the sample back and forth. So there is no flow rate to volume trade-off. So from that 200 microliter sample, you can capture for half an hour at a full flow rate if you want. Also, the sample is returned to the microplate after it's cycled, so you get the majority of your sample back. So as we're seeing here, it's doing a 96 set, so 96 flow at once. That the printhead can then undock from the chip surface. The needles can go to a new well, pick up new sample, and the printhead will index to an additional array location. If it does that 4 times, it creates the full 384 high-density array you're seeing here. This is a schematic of the way that works. Is the pink vertical rectangles are each individual flow cell of the 96 manifold. The blue horizontal rectangles are the interspot references. So these are used for real-time referencing, and they are not printed to. So they're just on the surface of the chip or the capture surface, if that's what you're using. If you do 4 nested prints, you end up with the array schematic that's below, where we have these 4 rows of 96, and then there is the 48 interspot references. Each reference, there's 4 above and 4 below, so those are the ones that are used by default by the software. And so the other fluidic module, so the 96-channel manifold can undock robotically from the surface and move out of the way, and that enables the single flow cell to dock. So this flows one solution over the entire chip surface. So say we're activating the chip surface here with our EDC sulfo-NHS, for example. And then the array is printed. Then the single flow cell can then come back and dock and inject one solution over the entire array surface. So this is where you get the one-on-many analysis. So if that was, say, an antigen injection, we would be getting kinetic information from that concentration of antigen, that 250 microliter volume, to all of the antibodies immobilized on the array. Also, if this was an epitope binning experiment, we would be getting competition information for all of those 384 immobilized antibodies from that one volume of sample. Also, you can use the single flow cell to immobilize what we call a capture lawn, which would be, say you have an anti-FC antibody. You want to put that on the entire surface of the array so that you can then capture your antibodies from a crude solution using the 96-channel side. Then you come back to the single-channel side to do your kinetics analysis. Just showing this, the same array schematic where we're injecting one sample over everything. So this architecture makes the LSA really ideally suited for some of the core applications in antibody characterization, those being kinetics and affinity analysis, competition-based epitope binning, peptide or mutant mapping, and quantitation. So in addition to having this hardware architecture that makes these assays very fast and efficient, we've also put a huge amount of effort into designing and implementing analysis software that really does an excellent job making the analysis very fast and powerful, but also providing really good visualization tools to make the data sort of experience rich and easy to communicate. And we have some, especially in the epitope tools, some really interesting visualization tools like these competition matrices, we call them heat maps, and these network plots that show the competition profiles about how the antibodies relate to each other. So when designing a high throughput kinetic experiment, there's a lot of factors to consider. Obviously, your selection of chip type and how you prepare your capture surface if you're doing capture kinetics is fundamental. I'm not going to go into too much detail about capture surfaces today, but we will talk about chip chemistries. How you design your antigen concentration series is important. With the LSA, because everything's done in parallel, we typically like to do a broad concentration series, like 8-point 3-fold series that gives us really broad dynamic ranges in the ability of kinetics we can evaluate in a single assay. Also, how you design your array. One big advantage of having a 384 spot array, even if you don't have 384 antibodies, is that you can spot your antibodies in a dilution series or capture them in a dilution series, so you can be assured that you will have ideal densities for your kinetic analysis. Also, you have the opportunity to spot antibodies in fairly high replication often if you don't have huge numbers, which allows you to sort of power the analysis or actually perform kinetic analysis with an N. So you can calculate mean and standard deviations of your rate constants across true replicates instead of just using goodness of fit parameters to build your confidence in those values. But it's important to note that while the LSA really brings a new scale to these types of kinetic analysis, we're not changing SPR at all. And so we often refer people to this paper by David Miska in the Journal of Molecular Recognition from 1999, where he really outlines all of the key, or at least many of the key parameters of how to properly design and execute SPR experiments, as well as how to report the data. And we don't think anything's changed, and we're trying to be consistent with these sort of fundamentals that have been put forward some time ago. So diving a little bit more into it here. So this is a picture of a gold prism, or a glass prism coated with gold, and it has this hydrogel layer on top. So this is an actual LSA prism popped out of the cassette. But we're going to go into kind of a cartoon mode to talk about our chip surfaces and how these work. So we have the glass and the gold. The gold is inert and it produces plasmons. It's not really part of the biochemistry of the analysis. Then we have a hydrogel layer. This provides a three-dimensional space for the protein to bind. It's flexible, it's hydrophilic, so it wets well, and your injected molecules can have good access to the surface. And it prevents interaction of the proteins directly with the gold. So once we have a matrix on the chip, it needs to be loaded with carboxymethyl groups. And these provide a negative charge point for electrostatic preconcentration, which is a phenomenon that we use to get proteins to stick into the matrix so that they can be coupled. So first chip type I'll cover is what we call our CMD200M. This is a 200 nanometer thick, highly cross-linked carboxymethyl dextran hydrogel. So it's important to remember that when working with this chip type that it's not just little strands of dextran coming off the surface. It really is like a gel layer, and that can create some degree of diffusion barriers for proteins and analytes to get into the matrix. But it is our highest capacity surface, and we use it typically for doing interactions with very small analytes. So another sensor surface to go over is our linear polycarboxylate, or HC200M. So again, this is a 200 nanometer matrix, so it's the same approximate depth as the CMD200M we just talked about. But the big difference is that instead of having a highly cross-linked gel layer, we actually have these linear strands of polycarboxylate. So there's much less of a diffusion barrier for molecules to get in and out. It's probably roughly half of the protein capacity of the CMD200M, but it does have a bit better transport dynamics and is a bit easier to regenerate. So this is actually for low concentration samples or screening kinetics to sort of moderately small proteins, this is what we would use. A very similar chip type is the HT-30M. So this is, again, the linear polycarboxylate, but instead of being 200 nanometers thick, it's 30 nanometers thick. It's a medium protein capacity chip. This is probably our most commonly used general chip. The vast majority of either kinetics or binning assays you're going to run can run well on this chip type. And it has great transport dynamics, very similar to a planar surface and reasonable binding capacity. The last chip type we're going to cover is the planar dextran. So this is the same chemistry as the CMD200M shown earlier, but instead of being a 3D hydrogel, it's essentially a film on the surface. So this actually has probably the best transport dynamics of any surface we have, although it's hard to measure a difference between it and the HT-30M, which I actually have a slide on later. It's relatively low protein binding capacity, but it's actually sufficient for a lot of assays. We're starting to use these much more commonly. So if you have a reasonable sized antigen, say 30 kilodaltons or more, you're definitely going to be able to get enough antibody on the surface to get big binding responses and do things like binning and kinetics. So this is just a list of the catalog of chip types. I talked about most of these. The only ones I didn't mention is we offer streptavidin sensor surfaces and nickel NTA surfaces as well now. And this is what the chips look like when they're in the cassette. So you can see there's the glass prism near the top there. So a property of all laminar flow cells is that you have a bulk flow, and then as you approach the surface, there's actually no fluid movement. And so you end up with what's called an unstirred layer that molecules need to diffuse through to actually access the surface. So the rate at which those molecules can move through that unstirred layer, it's diffusion, but it can be described as a flux, which is governed by Fick's law. So you have a diffusion coefficient, a concentration gradient, and a distance that determine that rate. As the liquid gets more viscous or the protein gets larger, the hydrodynamic radius of the protein increases, the rate that that diffusion occurs is less. So if you have a very large protein, it's easier to create what we call a mass transport limited condition, where the binding rate observed on the surface is being governed or influenced by the rate of diffusion from the bulk flow to the surface rather than just the kinetics of the interaction. This is part of why it's good to do kinetics at relatively low densities, because if you think about it, if there's this mass action of analyte diffusing through this unstirred layer, and you have a low antibody density tethered to your surface, it's unlikely that you're going to be able to deplete that flux of analyte coming from the bulk flow down to the surface. But if you have a high density, especially if you have a high density of a high affinity fast on rate antibody, it can grab up all of that antigen that comes through, and you end up measuring the rate of antigen flux rather than the rate of the interaction. So there's two ways to compensate for that. One is that you immobilize low density antibodies or a titration of antibodies where you have low density spots so that you don't observe this effect in the first place. Also, we can add a KM term to the kinetic model, a mass transport model. That works well if the effective mass transport is relatively modest. Obviously, if you're having to compensate for a massive change in the kinetics, it's adding quite a bit of flexibility to the model, and the parameters will be a bit less constrained. This is a simulated example showing the same concentration injection over this 1 nanomolar affinity antibody. So it's a 25 nanomolar injection where we put in a significant mass transport term. You can see the difference in the binding profile. It really looks like a different interaction. These are some of the properties that govern that in terms of the dimensions of the flow cell, the viscosity, and this diffusion factor of the protein. here's an actual example of this occurring. So we have this clone C21 that we spotted onto the array at 3 very different densities. And when you zoom in, you can see we fit it to the kinetics model. And we see essentially a 10-fold difference in the apparent on rate going from a, well, modest density, it's not even really low density, to the high density surface here. And you can see how different the low concentration injections look on these two surfaces, where you're getting essentially saturation within 5 minutes from the lowest concentration on the low density surface. On the high density surface, you're not even at 50% bound. So it can make a dramatic difference. This was an extremely mass transport limited system shown here. But by titrating it down, even not to really low levels, but just to moderately low levels, we're able to generally overcome that. This was with a 63 kilodalton protein. And all of these 3 sensigrams you see are seeing the same injection of antigen. You know, this isn't a dilution error or something. This is actually in the same flow cell, the same antibody at different densities. In the very same experiment, we have another clone that was spotted at 3 different densities, and you can see it really made almost no effect on the measured on rate from those. So it's much slower. It's an order of magnitude more than that slower on rate, and it's simply sort of outside the range where the transport limitation occurs. You can see the data fits better at the low density, which is also a pretty common effect. We're probably getting some sort of crowding effects by having high density, but the actual kinetic estimates were not that different between those conditions. So it's both an antigen size and an on-rate dependent phenomenon about how much this mass transport effect can be observed. And it's also influenced by the chip surface somewhat. So to go into that in a little more detail, we'll cover recent publications. So this was a collaboration between Carterra, Adimab, and Amgen, where a bunch of the published or patented PD-1 antibodies were synthesized and analyzed on the LSA, the Biacore 8K, and 2 solution phase affinity measurement tools, the Kinexa and an MSD assay. This is an LSA run from that analysis. You can see this was, it was about 40 antibodies, but we wanted to fill out the 384 array, so we analyzed everything in 8 to 12 replicates for each clone. This was one run set up in an afternoon. There's 8 concentrations of the PD-1 antigen starting at 1 micromolar in a 3-fold serial titration. So to generate all of this data in an evening, we used 7 micrograms of antigen on the LSA. Real high-level summary from the results. When we compared on similar chip types the kinetic data from the LSA and the Biacore 8K, we got essentially the same kinetic value over a broad kinetic range. We were within 2-fold. The LSA was about 50 times faster, though, and used about 1% of the sample to compare. Also, there are error bars in the LSA direction because we generated multiple replicates of each data point, whereas the Biacore only generated a single data. So a little bit more into the meat of the paper, though. When we compared chip types, we found some interesting differences. So on this plot, you can see the x-axis is using that HC30M chip. So this is that 30 nanometer linear polycarboxylate surface. And we're comparing the on rate, the off rate, and the affinity. And that's compared to either the CMDP, which is the planar Dextran, or the 200 nanometer Dextran. So we see that the HC30 and the CMDP give very similar kinetic results. But the CMD200M, the thicker hydrogel with that cross-linked surface, actually showed a systematic decrease in measured on rate. The off rates were much more similar, and then the affinity displays that on rate difference. So this was really interesting to us because we now know that if we're interested in precise kinetic values, that especially for full protein antigens, that we really need to focus on these less matrix chips. We're going to get a more reliable kinetic analysis. This is not the first time this effect has been reported. The group at Pfizer did a study on their proteon looking at different chip types and saw a very similar result that was published back in 2011. So this is sort of a universal effect of heavily matrix chip types. So the LSA kinetic software is really built to handle thousands of interactions. It has automated batch processing tools to make you go from raw data to processed data in just a few clicks. It has a number of automated data QC flags to prevent common errors. If you're familiar with SPR literature, there's a lot of sort of dubious results appointed, either because the software will spit out a result and people report it, or there's some misunderstandings of limitations and constraints that people should have on that analysis. The software facilitates multiplexed analysis, so if you have antibodies from multiple projects or sources or multiple antigens you want to analyze, it allows you to define what everything is in the software and then very easily segregate the data sets that come out based on those. It has a number of really good visualization tools. I'll show a couple examples. And then there's a feature that will automatically export the entire analysis to an Excel file with multiple tabs. So this is great for e-notebooks or just sharing data where you get all of the figures and tables that you generated in the analysis software in this one document. So I talked about QC flagging of data. This is an example that highlights many of the features in the software. So the gray over on the right are clones that are below a threshold set. So we would call these non-binders. The software will automatically not report an on rate or an off rate or a KD value for these clones. So it's not something you would need to curate out of the data set later on. Also, if things have a poor fit, by looking at the residuals, it will flag those, shown here as yellow, as complex. So you need to assess whether or not you believe those values. It will give you the values, so it just flags them. And then same for these kinetic limitations. So the ones shown in purple, the top clone has a very slow off rate. I mentioned earlier that by default, the software has a 1 × 10⁻⁵ off rate limit. These clones hit that. So it's going to report the kinetic values and the affinity as a limit. It'll say less than 1 × 10⁻⁵, say less than 50 picomolar for the affinity. Similar here, we have an example where the software thinks we did not inject a concentration of antigen above the KD of the interaction that it's estimating. So essentially, you haven't injected a high enough concentration of antigen to fully describe the interaction. I think this clone was about 750 picomolar, and we only went up to 1 micromolar of antigen. So we were actually slightly above, but it's having a hard time estimating that because we don't have any sort of convergence in the concentration data. So it will flag things that you also may need to consider injecting higher concentrations. It will report rate constants for both of these kinetic limitations. It just flags them for you so you're aware of them. Another great visualization tool in the software is it automatically generates these Iso-Affinity plots. This is a really excellent way of viewing the kinetic diversity of your panel. So we have the off rate in the x-axis and the on rate in the y-axis. And the diagonal lines are what we call iso-affinities or single affinities. So the one sort of in the middle left is 1 × 10⁻⁹, or 1 nanomolar. Then we have 100 picomolar going up to the left and 10 picomolars up in the corner. So the higher affinity clones are to the upper left and the lower affinity clones are to the lower right. You can see a number of clones are pegged against this 1 × 10⁻⁵ limit that was set as a limitation in the software. If we didn't have that limit and you had a flat line, the fitting algorithm could essentially pick any value less than that and the data would fit equally well. So it could say you have an off rate of 1 × 10⁻⁹ or something, even though it's just essentially measuring nothing. but the residuals wouldn't change, so the fit wouldn't know any better. So we have to give it some constraints to operate in. And unfortunately, there's examples in the literature where software will fit it that way, and people have reported some relatively high affinity clones, let's say, based on those erroneous fittings. So typically in this type of assay, we can see at least a 20,000-fold dynamic range in affinities across with one of these 1 micromolar to 450 picomolar kinetic series antigen concentrations that we run. So in summary, the LSA really provides a unique approach to high throughput screening and characterization, really combining the concepts where instead of just doing low resolution kinetic analysis from your early small scale crude samples, you can get a full kinetic profile and characterization for a large number of clones with very limited amount of material. And also, just to reiterate, the LSA has not reinvented SPR as a tool or a strategy. So the same rules apply for good practices, and that you need a lot of attention to detail in terms of the way you set up these assays and the way you report results to get good and valuable results. So with that, I want to bring up that you can tune in to more Carterra content. We have some recent webinars on kinetics and epitope binning. So if you go on YouTube and search for the Carterra channel, you can find those there, watch them. Also, I want to advertise that next week we have a free CHI webinar that's hosted by Twist Biopharma, where Aaron Sato, their CSO, is going to talk about their synthetic library platform, and we'll also talk about the LSA and how it fits into the screening workflows for those. That's next Wednesday, April 29th at 11 a.m. Eastern Time. And you can find a link to register at carterrabio.com/events. So, thank you all for your time. I hope you found this interesting and useful, and I hope you all stay safe. So hopefully we still have some time for some questions. Thank you all.
Thanks, Dan. That was a great presentation. We have some questions that came in. If you have any more, please send them via private chat to me, the host, John McKinley. Here's a question. How do I know if the antibodies are immobilized at too high of a density? Second part, what can you do to ensure that capture levels are appropriate for a screen?
Yeah, so the one way you can tell if things are at too high of a density and you're getting lots of mass transport limitation is if the model just doesn't fit well. There's kind of a characteristic profile you'll see where the slopes of the association look more linear than you would think they should. Also, if you have the ability to spot at multiple densities, you'll see that that profile changes as you go to the lower density. So that's the telltale sign of mass transport limitation. And the other part of the question was, how do you ensure that you're capturing at the right density? So there's a few strategies. The best and the easiest is to immobilize at multiple densities. Then you can pick and choose. You would use probably the lowest density spot you have that has a good, enough information to get a good kinetic fit, or maybe the lowest two if you have multiples. The other option is you can control the way you create your capture surface so that it doesn't have the capacity to bind really large amounts of antibodies in the first place. Very often that's an approach people need to use if they have large numbers of crude samples that vary widely in concentration, is you can create a less dense capture surface and then try to flow for a long time so that you sort of achieve more of a saturation of that surface and can have a more comparable and uniform binding level of the antibodies across the array. Thanks, Dan.
We have another two-part question here. Can the SPR response be used to estimate the stoichiometry of an interaction? Does the binding level in RU correspond directly to mass?
Yeah, it does. So what we're measuring is that change of effective refractive index at the surface. But because on these matrix and these chips, everything's sort of randomly oriented, most proteins give a very good mass to SPR signal response. So if you immobilize or capture a certain level of antibody using the mass ratios between your ligand and analyte, you can estimate the observed stoichiometry of that interaction. There are examples mainly of small molecules that are highly optically active where the SPR response can actually deviate a bit from the mass. That is extremely uncommon, almost unheard of in proteins.
Okay. Another question. Does the source of an antigen for kinetics run need to be purified?
Interestingly, no. So what the important thing for using kinetics or for antigen in kinetics is that the antigen needs to be homogeneous. So if you have, say, folded and unfolded forms in a prep of protein, almost always you're going to see a non-one-to-one interaction profile where you have different rates associated with those different protein forms. Also, similar things can happen if you have epitopes that are affected by glycosylation. You have different differential glycosylation in the antigen. You can see these heterogeneities or small amounts of aggregate, or if it's dimerized partially in solution, you'll see non-one-to-ones. But if you have, say, 293 cell expression system that's producing really high quality protein, and you can accurately estimate its concentration, you can potentially use supername as the antigen form, because assuming the antibody is specific, all you need is that concentration series. Very typically, the relative matrix components from the media won't have a significant effect on the analysis. So it's really more important that the antigen is effectively homogeneous in solution than it is pure.
Okay, another question. Does the relationship between size of the ligand to be immobilized and the RUs immobilized to reach desired ligand density?
Sorry, can you read that one more time?
A question regarding the relationship between the size of a ligand to be immobilized and the RU. Yeah.
Yeah, so I think this is just basically similar to the stoichiometry question, the mass ratio. So because the signal to mass ratio is essentially 1-to-1 in SPR, you can estimate it. So if you have a 150 kilodalton antibody with 2 binding sites, and you immobilize that on the surface, you can estimate, okay, of a 10 kilodalton protein should bind, it should be, well, let's say 15 kilodalton protein, should be 10 times smaller than the antibody. So the antibody, the binding response you would expect to see would be 10 times less than the amount of antibody captured, well, times 2, because the antibody is bivalent and should be able to bind 2 molecules of antigen. So you'd see essentially a 5-fold decrease in signal. So if you captured 100 RU of antibody, you would expect to see 20 RU of antigen response at saturation from that 10 kilodalton protein. So you can pretty much work it out on paper before you run the experiment. Some proteins will immobilize in a less than 100% active state if you covalently couple them based on the extent of lysines in their CDRs. But you can always use capture systems. Like for antibodies, we use expression tags or anti-FC captures that usually have very high levels of, close to 100% of the amount of antibody that's captured be active for binding antigen. So those calculations can work out really well.
Thanks, Dan. Well, we've reached the end of the hour, and we'll make sure to reach out to you for any of the questions that we didn't have time to answer today. Here at Carterra, we're working with the Bill and Melinda Gates Foundation and the La Jolla Institute of Immunology to screen hundreds of antibodies that target COVID-19 and rapidly move these therapeutic candidates to the clinic. If any of you are screening antibodies for COVID-19, please contact us to discuss how we can support your program. Also make sure to join us in next Wednesday's webinar at the same time with Twist Biopharma to learn how they use the Carterra LSA to screen and characterize large panels of antibodies. Thank you all for joining us, and thank you very much, Dan.
Yeah, thank you, and thank you all for joining. I hope you found this useful. And stay safe.